A little while ago, I saw this amazing proposal for a project which would allow a probe to be launched from Earth orbit and bounce around the solar system using various maneuvers to then catch up with Oumuamua, which passed us a number of years previously. So this is the example of the trajectories here. Here, the red is the probe. This yellow is the path of the interstellar object, which has already passed us. And so the probe goes spinning around and goes out, reaches Jupiter, drops right back in, skims close to the surface of the sun. As it does so, it fires its propellant and goes whizzing off and catches up, which is absolutely incredible. So the precision involved to do this must be amazing, and if it was actually done, but also just like how can you come up with that kind of trajectory? So I was intrigued to know whether or not WeightShift could manage to do something similar. So WeightShift basically it's a way of generating animations based on target trajectories, if you like, and is a completely configurable system. So for example, here we got a target trajectory, which is this movement of the blue box as I just scrub backwards and forwards. I mean, it's just an indication for how this creature might move, and I've built the physical version of the creature. We can actually set it solving, and it solves this scene in a few seconds. So it's going to figure out how to move this object around to basically follow the blue target trajectory. So now it's done it, and it generates this kind of trajectory. But you can build anything. So this can be used for like tracking trajectory of physical, full physical characters, or maybe tracking trajectory of those characters, but moving on a moving platform, like in a train bouncing around. It can also be used to solve like initial value problems. So for example, here we've got a situation where the target animation on the blue board is basically the target animation has the white ball starting in one place, and all we're going to require is the red ball goes into this pocket, and the system is basically configured and set up so that it's able to hit this white ball in any direction it likes, and in so doing, it pots the blue ball. It pots the red ball in the pocket it's meant to go to, and I can move this ball around. Whoops. I can remember how to use Maya, and let's just put it over here, and we can tell it to solve again. So it will solve a new situation. You can really change anything you like in the scene, and it will try to solve it. So was it on it? There we go. And fortunately, it solves it. Okay, so the idea could I set up a simulation of the solar system inside WeightShift and basically use it to like calculate what firings of some rockets on this probe would then end up being able to essentially launch it off into one of these crazy slingshot types trajectories that allow it to catch up. So I won't close that. So I didn't actually set it up in Maya. It was actually easier for me to set it up in code. So that's what I did. So I built myself a solar system inside WeightShift. Had to do some scaling so that it could all be kind of like simulating with reasonable scales and so on. So what we're seeing here in the middle is the sun. So I should say the sun has been made 4 times bigger. All the planets have been made 400 times bigger. So all the planets have got consistent scaling. So you can see these, the sort of giant planets are absolutely huge compared to the inner planets. So here, we've obviously got Mercury and Venus and Earth and Mars. And there's the gap and so on. We go out. Okay, so we've also got down over here, we've got our interstellar object with a tricky to pronounce name. And if I just set this simulating, actually it's actually playing back an already calculated trajectory. So we can see our planets whizzing around, and we can see our interstellar object come through this funny angle. It comes around, goes around the sun, goes whizzing off. And we're set up to simulate. So basically one frame here is 1 day. So let's go back to the beginning, and as I scrub down. Basically, we start our simulation. We've got about a year, around about 365 frames, and the interstellar object reaches its perihelion. Okay, and you can see in that time the Earth has made a complete. The Earth is the green one, has made a complete orbit of the Sun. So scrub forwards for 1 year. Here we are. Okay, so this simulation, all the planets and the Sun, indeed, and the Sun itself and so on, are all dynamic objects. They've got no collision. They're all being simulated according to Newtonian gravity. So maybe missing some effects, but that's what it's got. Actually, if you look really closely and zoom in, you can even see the Sun like wobble around in its center, which is kind of quite cool. Okay, so everything's simulated. 1 frame is 1 day. We actually run it with 4 sub-steps, so each simulation step is about 6 hours. We also include our satellite. Actually, I should also say there's also the moon, the Earth moon, which goes around the Earth. Because the Earth has been scaled up by a factor of 400, it's kind of like you can't actually see it. But anyway, it's there. So let's go back to the beginning, and we can play. Let's play in like super slow. And what we're going to see is for the selected objects, which is the interstellar object and the probe, which is really close to the Earth at the beginning. I'm just going to show their trajectory over a week. So the line just goes from the current time to 1 week in the future. So we can see we start off with the probe. It's kind of near Earth. It's actually slightly kind of out of orbit of the Earth. So it's on its own. It actually drifts. It starts to drift away. It starts off about the same distance as the moon from the Earth, but on the other side. Yeah. So it goes and it's orbiting around, and obviously by the time, for the first 2 years. We imagine we haven't launched the probe yet. Yeah, so the first 2 years it has no control. After 2 years, it gets to fire its drive, and it's allowed to exert 0.1 newtons, so 100 millinewtons, and sort of continuously between 2 years after the start of simulation and 7 years after the start of simulation. So we got, I'm going to assume we can fire this stuff for 5 years. And it can, the system is allowed to basically pick the force and magnitude, the amount of force it's going to use, and adjust it every month. So it has to sort of pick a new value for a month, and then it simulates with it, and so on. And the goal is to basically catch up. You can see it's going over here. We're wherever we are, 5 years or something like that into the simulation, and the probe is out over here, and there we can see the interstellar object is way out over there, and so it's going around. Actually, we'll see. So we see it's gone way out. Actually, it's gone out to the orbit of whichever that one is, Jupiter, I think. And it's going to drop in now. Of course, with Adam Hibbert's trajectory, it actually uses this planet to slow it down. Here, I think it's using its propellant to slow itself down, and it comes back in, goes really close to the sun, and goes whizzing off, and it goes off in the right kind of direction. So I'm actually going to scrub back to the beginning, and we're going to see a little bit more of the trajectory. So we can see here how much of the trajectory we're going to see. So 1,000. We're going to basically see where it is now and where it's going to be for the next 1,000 days. And the same is true of the interstellar object. So we can watch them coming past. So let's go back and start simulating. Just speed it up a little bit. So you can see as it goes through, we're actually still orbiting around. You need to look at the beginning of the line. But it's now starting to fire its boosters, and it nudges itself out of orbit around the sun, goes out, then drops down and kills off its speed as much as possible, and then drops right back to the sun. And really accelerates and goes off and tries to catch up. Obviously, it's not by any means perfect. So it's going to slightly miss. But let's see if I can go a bit closer. I'll just scrub to the end. Okay, and we'll, whoops. That's that one there. Am I going to be able to find it? No. Okay, now I've lost. Oh no, I've lost where we are. But anyway, oh, of course. So when we get near the end of the simulation, then we don't have much trajectory to look at. So I wasn't able to find it. So let's have a look here and see if I can find it here. There we are. So now we're kind of quite close to the end of the simulation. It's a bit difficult to see exactly how far apart they are, but they're kind of in the same general vicinity, especially compared to how far away they are from the sun. So yes, I was actually pretty pleased that it comes up with a trajectory that looks interesting. If it only used its motors on its own, it wouldn't be able to make anywhere near as much of a catch up. So it kind of does pretty well to exploit this nature of going around near the sun. I should say this is absolutely not a realistic proposal simulation. There's so many approximations in here. I've been totally, I have no idea whether or not. Well, I think that the force exerted is sort of vaguely in the right kind of area, but whether or not I doubt it's feasible to apply it for so long and all the rest of it. That's one thing. And then the second thing is actually I think that this slingshot trajectory here is actually exploiting an instability in the solver, because the reason I say that is because we can actually see now. I'm going to show where so this is overlaying on top of the output. It's overlaying a graph of the X, Y, and Z components of the thrust force being applied to the probe, and we can, as we scrub here, you see up here there's a little cross, right? At the moment the controls are being the control is at the top and so on, but there's no actual thrust being applied. The thrust is only going to be applied between kind of here, so it's time in the horizontal axis for this graph is between the sort of 2-year mark and the 7-year mark. So at this point, it can wiggle its controls or whatever, but there's no thrust being produced. So it can start to apply the thrust around about now, and so on. So during here, you can kind of see that, as a result of this sort of this thrust application, the trajectory is getting distorted and so on. So doing a bit of orbiting and a bit of thrust, and you can see as it's going out here to this point where it's like really slowing down. Then, in fact, this actually applying you can't really see from this graph because there are 3 lines on top of each other, but it's kind of applying a force in this sort of negative X direction, and so on. But actually, this point here is the last time it can apply a force. So actually, by the time it starts dropping back towards the sun, it's entirely ballistic. And I would have expected, if this was an accurate simulation, that it should end up basically following an orbital trajectory, but it doesn't. It kind of clearly somehow gains a little bit of extra speed and is able to actually slingshot itself out. And I don't think that's realistic. So I think what's happening is that the simulation is using this symplectic Euler integration, which is like super stable, super accurate, so long as the time step is above a threshold. So you can see these planets, they basically orbiting, they orbit around the sun, and they just stay in their steady orbits. They, right at the end of the simulation, I guess I should have checked this before I started. The Earth is kind of here. The green Earth is coming in here. If we go back to the beginning of the simulation, whatever it is, 30 years, the green Earth basically comes and it's pretty much in the same place. So for the kind of normal orbits which don't go too near the sun, the simulation is like really accurate at preserving the energy. But because it's going so fast and it's going so near the sun, I think it's actually gaining a little bit of energy as a result of inaccuracies in the simulation. So yeah, so it's making this really cool slingshot maneuver. It's getting its energy from what I think is an invalid source, but actually I still think it's pretty cool that it's able to exploit a opportunity in the system to gain this energy. And yeah, so anyway, I thought it was quite interesting that it's interesting to push this this generic solver and see what kind of situations it can solve. I was quite pleased that it actually generates something which looks certainly interesting.